Hello and welcome, Alessandro. Uh,
Hello,
it's a good to have you here, and I guess you are joining us from Italy, somewhere north.
indeed. Yeah, indeed. From the University of Padua. Thanks for your invitation. I'm really happy to be here today.
And yeah, it's good to have you here. And this is the last, but I guess one of the most important lectures or topic to 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 know about. And it's about privacy and security, I guess. And please feel free to start when you are ready, or maybe you can talk about more about yourself and what you are doing and so on, so people know more about you.
Sure. So, again, thanks for having me here. Today we're going to talk about security and privacy in the Internet of Things. So we'll first cover a bit basic stuff related to security and privacy, just to give you an idea of what we're talking about and why security and privacy it's both an issue in the Internet of Things and why it is different from other type of network that's not Internet of Things. So just to give you a brief introduction on who I am, my name is Alessandro Brigente. Currently, I'm a postdoctoral researcher and adjunct professor at the University of Padua in Italy at the math department. My research interests cover different areas in the wireless communication and mostly cyber physical systems and the Internet of Things. Currently, I'm also starting to dig a bit more into distributed ledger technology, blockchain, this kind of stuff, and mostly the application of this technology to the different domains. So, related to Internet of Things, so let's start with this security basics. So, whenever people talk about security, there are three important concepts that one should account, which is known as the CIA triad. Okay, CIA, this acronym that stands for confidentiality, integrity, and availability. Okay, these are three important things that we want to have in our systems, in our network, in our whatever it is, and we want to provide full security to the system. Okay, so when we talk about confidentiality, this is the very first thing. Confidentiality is hiding the information from unintended receivers. Okay, so you see that already here we might have some problems. Confidentiality means, again, that we want to hide the information from unwanted receivers. So if we are talking about a wired network, it might be easier to provide confidentiality somehow. Okay, we can decide what are the parties involved in the communication that can actually receive packets, receive the information we want to deliver, right? Because we just connect the cables. If we have a cable, we connect two devices. More or less, we can provide confidentiality to the communication in there, unless someone goes there, the cable basically drills a hole in the cable and starts eavesdropping communication, then the confidentiality is not there anymore. But still, a cable provides good level of confidentiality. If instead we are talking about a wireless network, which is the most common situation when we're talking about Internet of Things devices, we already see that we have a challenge in here. Providing confidentiality through the wireless network is not as simple as providing confidentiality in a wired network, right? Because the transmission environment is open. Okay, whoever is there in the space might be able to gather some packets and be able to infer the information that we want to transmit. Okay, so we have different ways of providing confidentiality. One of them is through cryptography. For instance, we can encrypt the information through some sort of keys. Okay, we can have either symmetric or asymmetric keys. The point is that we have a secret thanks to which we are able to hide information, and just intended receivers that know this secret are able to decrypt the information, then for read whatever it's written inside the packet. Okay, so this is just to give you an example on how we can achieve confidentiality. Okay, the second letter, the I, stands for integrity. Okay, integrity again is something that is crucial for secure communication. Integrity means that no one is able to modify the content of the packet. Okay, so basically, what we want to ensure when ensuring integrity is that, for instance, I am the transmitter, we have a receiver, I'm transmitting the packet, and the receiver receives exactly the packet that I've been sending. Okay, so there has been no modification in the content of the packet during transit. Okay, so also here providing integrity might be a bit challenging. So again, thanks to cryptography, we can ensure the integrity of communications. So for instance, we might have some functions, some hashing functions, for instance, that provides us with the proof that the packet has not been corrupted during transit, or that there has not been is dropping the communication, and therefore someone that captured the packet, then modify the packet, then injecting again the packet inside the network. Okay, so different proofs that you might have in order to be able to check that the packet is the one that is being actually sent. This is crucial. This is really crucial in integrity, because when we are sending packets, if we are talking about safety critical communications, we do not want any part in the network to be able to just modify packets, right? If anyone is just able to capture a packet, modify the content, and then deliver a packet as if it was sent by the legitimate transmitter, you see, we might have really huge problems. We might be able to modify the devices that are able to communicate within the network. We might be able to have privilege escalation. We might be able to provide, therefore, opportunities for outsider attacker to be able to inject malicious traffic within the network, and therefore modify permits, this kind of stuff, right? So again, also integrity is really important to be ensured when we're talking about security. The last letter, the A, stands for the availability. Okay, availability, it means that we have, so whenever we're dealing with the network, with the system, we have a system, a service that we want to deliver, right? So for instance, in a communication network, our service is the communication that we are able to guarantee to customers, for instance. Okay, so having availability of this service is really important. Basically, if someone is buying a service, we want them to be able to use the service, right? So the availability should be there. But availability is something that might be really difficult to deal with. Okay, so indeed, for instance, when we're talking about denial of service attacks, denial of service attacks are specific attacks that target the availability of the system. If we have a denial of service attack, it means that, for instance, we are not able to communicate anymore with the other parties in the network, with the other devices that are connected to the network. Okay, and indeed, denial of service attacks are really hard to be dealt with. Okay, and therefore we need methodologies, we need solutions to counter these attacks. Okay, so all the methodologies that we might envision to provide security needs to take into account this CIA triad. They need to provide confidentiality, integrity, and availability. We would like to have a solution that provides these three features all in one. Now, what makes security critical and challenging for the Internet of Things? So we have these three features that we want to ensure, but are we sure that these are, first of all, is this the correct order? Do we first want to provide confidentiality, then integrity, and then availability, because we think confidentiality is more important than integrity, for instance? Or do we need to order these features in a different way? Okay, so this is the first question. The second question is, usually we have devices that have high computational power, high memory. They do not have problems with battery. We can just connect the devices to a power source, and then we're done, right? But this might not be the case with IoT devices, right? So we need to take this into account. Okay, so first thing related to the ordering of the CIA triad, it depends. It depends on the use case, right? So if we are talking about IoT, and in particular the application of the IoT to industrial control systems, cyber physical systems in general, then here you see that availability is the first thing that we want to guarantee. Why do we want to guarantee availability as a first thing? Usually in cyber physical systems, we are dealing with safety critical networks. Okay, so people usually trust these systems, and this trust also may come at the cost of the safety of the user itself. Okay, so imagine that we are talking about a car. Okay, inside the car, we have a bunch of sensors and actuators. Okay, so the different devices within the car may be seen as IoT devices, right? So if an attacker is able to undermine the availability of the car, it might be the case that the user is not able to brake, or the user is not able to steer. right? So it's really critical to provide availability to this kind of system. On the other hand, confidentiality might not be as much important as availability, right? So again, if you're talking about the car and the information that flows within the car's network, confidentiality is not that critical, right? What is the information that flows within the car? Information is brake at this time instance, steer the wheel at this time instance, speed up at this time instance. So nothing that an attacker would really care about to a certain extent, of course. But if we need to give a priority to this CIA trial, then I can we can safely say that the availability is more important than confidentiality in this sense. Okay, so
Sorry,
this is the first question.
I'm sorry. Since you were talking about different concepts, I had a question before, but I did not stop you. But since we are
Okay.
talking about different concepts in security, and we saw that you were talking about this CIA triad, where we have confidentiality, integrity, and availability. So I have two questions. So are these three connected or part of the security? And the second one is where this privacy comes into the picture, or is it related to this CIA triad at all?
Yeah. So uh, when you ask whether they're connected, you mean connected one another? If confidentiality is connected with integrity and so
Yeah.
forth? Okay. Yes. Um, so what we can say is at the first look, they're not connected, right? They're dealing with different stuff. Confidentiality means that we want to hide information. Integrity, we want to be sure that the information is correct. And availability, that the system is working, basically, right?
Mhm.
But what we can say is that if an attacker is able to undermine one of these, it might also be able to impact the other ones, right? So let's imagine, for instance, that an attacker is able to jeopardize the confidentiality of a network, right? So it means that an attacker might be able to gather sensitive information from the network, right? So, for instance, might be able to gather information on who are the users that are dealing with the network, might be able to infer IP addresses, MAC addresses, the type of protocol that is used by the network itself. And now I'm giving this example on the network, but might be many different use cases. Just dealing with the network because I guess it's the field where most are confidential with, um, are familiar with. So if the attacker is able to gather such kind of information, now the attacker has a lot of information on the network, right? So for instance, if the attacker sees that the protocol that has been used by the network is UDP, then there are specific attacks that the attacker may use to undermine the availability of the network, right? There are the specific kinds of denial of service attack that can be launched based on the fact that the network is using UDP protocol. Okay, so in this sense, we can say that this CIA triad deals with the different features of the network, but there is a cascade effect. Once one of these features is missing, then also the other might be not there anymore, might be jeopardized by a clever attacker.
Mhm. And also, since I was asking about privacy, there was a question about privacy as well on Discord. So it would be interesting to know your view on the privacy aspect, especially uh, during the data transfer between the devices in the context of IoT. And he was interested to know this because it's hard to find solutions that can mitigate adversary attacks in IoT, like side channel attack and something like that.
Sure, sure. So, going back to the CIA trial, when we're talking about privacy, we are talking about the confidentiality. Okay, when we are able to ensure confidentiality, more or less, we're able to ensure privacy. Why am I saying more or less? Because now we are dealing with IoT, right? We have use cases, we have side channels, we have threat vectors that we didn't have with the previous, let's call it previous generation networks, which was not the IoT itself. And this is another thing that makes IoT challenging, right? We have privacy concerns that were not there when we weren't talking about the Internet of Things. And let me move to this slide because this helps me in responding to the question. So when we're dealing with IoT, it means that we are dealing with a lot of use cases, a lot of different use cases, right? So for instance, IoT might be applied for intelligent transportation systems where we have cars that are IoT nodes. Then we have the use case where the UAV is a IoT node, right? We have drones, swarms of drones that need to communicate, but then this might be IoT nodes. And then we have the use case where IoT is used in industrial context. So one important thing, one important consideration that we might do for IoT is the fact that in a lot of use cases, IoT is collecting a lot of users' sensitive data. So let's imagine, again, in the context of a smart city, we have houses with a lot of sensors, right? A smart home collects a lot of sensors on, for instance, the power usage of a user, right? This power usage then is reported to a smart grid infrastructure that basically deals with billing. Okay, so for instance, it might be used for billing. So here we might in a classical system, in a classical way of providing confidentiality, as I was mentioning before, we can use encryption, right? So if we use encryption, it means that whatever information on the power usage that we are providing to the smart grid, it's hidden from unwanted receivers, right? Just because we have packets that are encrypted with some key, okay, some cryptographic protocol, right? So this information should be safely delivered, providing confidentiality to the smart grid. Still, due to the fact that we are dealing with the Internet of Things and due to the fact that we are dealing with the user-sensitive data, this form of confidentiality has been proven not to be sufficient. Why is that so? Again, let's imagine we are talking about the smart home. By just looking at the encrypted traffic, we might see whether a user is inside the house or not, right? If the user is turning on light bulbs, then these are generating some packets that are encrypted and then reported to the smart grid. That's okay. Still, we see that the smart home is generating this type of packets, which means that the user is inside, right? So this is one of the challenges that we have when we are dealing with the Internet of Things and all the new use cases that IoT is enabling, right? Uh, so yes, when dealing with privacy, we have a lot of problems in the IoT. Indeed, later on I will show you a specific application where we want to deal with privacy, in particular the privacy of UAVs. The challenge will be that providing privacy to the user may not always be the best option. Because when we are hiding information, we are not hiding information for the user itself, but more or less we are also hiding information for critical infrastructure or for some other parties that should receive information from the IoT device. But I will go back to this later on. So going back to the challenges that we have when we're dealing with security in the Internet of Things, why do we have challenges? So the first challenge is due to the fact that we have resource-constrained devices. If we were talking about supercomputers or just home computers, we do not have that problem, right? Home computers have a sufficient amount of power, a sufficient amount of memory, a sufficient computational capability, and all these things are not there for IoT devices or might not be there for IoT devices, right? Why is that so? We have mostly we're dealing with battery powered devices. We cannot afford operation with huge computational complexity because that would drain the battery in a rather short time. And from a security point of view, this is really a problem. It provides many challenges, right? So, for instance, one of the pillars of security is using keys that are long enough. But keys that are long enough, it means that they occupy a lot of memory. It means that in order to encrypt and decrypt with these long keys, consumes a lot of power. It also means that we need to have the computational capability to be able to deal with this type of algorithms, right? This might not always be there for IoT devices. So whenever we are dealing with the with security, we need to take into account this resource constrained nature of IoT devices. The other thing is that mostly we are dealing with wireless communications. As I was saying before, wireless communication provides challenges due to the fact that the medium is open, right? Although we are communicating between two parties, whoever is within the range of communication might be able to eavesdrop the traffic, might be able to capture packets and therefore sensitive information of the user, right? So this is a further challenge that is due to the fact that we are dealing with use cases in the Internet of Things. And then the other problem or challenge is that most of the IoT devices might be dynamic. Okay, as I was mentioning before, we have cars that might be seen as IoT nodes. We have UAVs that might be seen as IoT nodes. We have industrial control systems that have sensors and actuators that might move inside the factory. Right, we have these robots that are able to move and that might be considered again as IoT devices. So when we're dealing with mobility, we have a lot of challenges. So for instance, let's imagine, no, let's consider the use case of the intelligent transportation system. We have cars that need to move within the road infrastructure, but now how can we manage key sharing? For instance, how do we securely share keys to all cars? How can we ensure that we do not have fake identities? How can we be sure that an attacker is not physically tampering the device, therefore jeopardizing the safety of users, right? So we have a lot of challenges, mostly due to the different use cases, but these use cases are enabled thanks to the Internet of Things. So we have this dualism for the Internet of Things, right? It enables new use cases, but together with the new use cases, we have also new threat vectors and increased attack surfaces that we need to deal with.
But I guess since you are also talking about security challenges in the context of, let's say, communication, and since there are many different possibilities or ways to communicate between the IoT devices or between the IoT devices and the gateways and so on. So I guess these communications or different types of communications face different types of challenges as well, right? In terms of security.
Yes, definitely, definitely. Indeed. So when we're dealing with this type of devices, as I was mentioning, they are resource constrained, right? So traditional protocols, for instance, let's talk about communication protocols, were not good anymore, right? We cannot afford to have TCP um, to use TCP protocols with for communication, right? So we have a bunch of new protocols that have been developed for the IoT. So for instance, LoRa, LoRaWAN, Sigfox, all these protocols that are new and that are specifically designed to work within the IoT networks, right? So researchers, developers, they created these new protocols, but together with new technology also come new threat vectors, right? Because so the fact that we are creating novel technology, it doesn't necessarily means that it comes with security guarantees, right? It's really difficult to create a secure system, a secure protocol, something that provides
Yeah.
security by design. There's always someone that is better than us somehow and is able to find vulnerabilities in our products. So this is another challenge, yes. And again, this is something that we have specifically because we are talking about IoT devices that have some constraints. So another constraint, for instance, is the range of communication, right? We have protocols that need to deal with the fact that IoT devices are not able to cover kilometers wide areas, right, with communications. And so again, we have new threat vectors, new attack surfaces, and another really challenging fact about IoT is that usually we are talking about a lot of devices, right? We do not have a network with 10 IoT devices. We have maybe 100 of devices deployed in the field, right? And so you see that if we were just dealing with 10 devices, they would have been distributed in more or less a confined geographical area. But if we are talking about hundreds of devices, the geographical areas over which they are distributed is definitely larger. And this provides an increased attack surface for potential attacker, right? We might be able to control those IoT devices and that are close to our infrastructure. But if we have IoT devices that are placed far away, we are not able to constantly monitor them to see whether someone is physically tampering them, for instance. Right? So again, challenges that are due to the fact that we are considering this specific type of networks. So as you see, when we're talking about security and privacy in IoT networks, we have a lot of challenges. And it would be nearly impossible to cover um, all considerations of security and privacy in the Internet of Things. So instead of providing you a list of possible attacks or possible use cases where we just have lists of threats and solutions, I want to show you three specific case studies that we developed that are specifically target specific functionalities of IoT and some of the specific constraints that we have within the IoT networks. Okay, so here you see three different case studies. The first one is the attack to 6-stage network formation. So here, as I was mentioning before, and as we were discussing, we have new protocols that have been developed to deal with the fact that we are considering IoT devices, resource constrained devices, and the fact that we want them to be able to self-organize the network. They need to be able to join new networks. They need to be able to let other nodes in the wild to be able to join the network, right? We have these dynamic networks, and therefore we have specific protocols devoted to these tasks. But again, as I was mentioning, the fact that we are using new protocols, it doesn't mean that they come with security guarantees, and then we will analyze the security of this specific protocol. Then we have the second attack, which is jamming attack, which deals with the fact that we were discussing the fact that we have mostly wireless communications. Right? When we're talking about wireless communication, not only we have that other nodes that are there in the wild that are within the communication range are able to overhear the communication, but they might be also to disrupt the communication of legitimate devices, right? So if we have a cable, it's difficult to generate interference in a cable, but if we're dealing with a wireless environment, it's really easy for an attacker to create jamming attacks to basically lower the signal to noise ratio at the receiver and for prevent the correct reception of packets. So we will deal with this type of attacks. And the last one, last case study, is the one that I was mentioning on the privacy and safety trade-off. Here we will dive deep into the privacy problem of the Internet of Things, and in particular on its application to UAVs. So here we will see that UAVs need to have privacy to preserve their privacy, for instance, on their location. But if we just hide the location of UAVs, then we might have a lot of problems for a critical infrastructure, for instance, that needs to understand whether a drone is approaching, right? So we will deal with this privacy issue within the IoT. So we start with this 6-stage network formation. So why do we have this new protocol? Did we need a new protocol? So the first thing is that when dealing with IoT networks, we are dealing with a huge number of devices, right? As we were mentioning before, we do not just have 10 nodes that form a network, but we might have hundreds of nodes forming the network, right? So IPv4 might not be sufficient. We might not have sufficient addresses to deal with such huge networks. So researchers started to move towards IPv6, right? So to have a larger pool of addresses that might be used. So this 6-stage network is indeed the application of IPv6 over IEEE 802.15.4e with the time-slotted channel hopping. What does this thing mean? When we're dealing with channel hopping, it means that devices need to select a communication channel that they want to use. Okay, and in particular, we have different ways of performing channel hopping, but in this context, we have that nodes might choose the transmission frequency they want to use for that specific communication over a set of possible frequencies, right? So for each communication, they're hopping from a sequence to another according to certain sequences. Okay, and in particular, when we're dealing with time-slotted channel hopping, it means that time is divided into slots, and in each of these slots, the node might be able to choose the new frequency to use for communication. Okay, so the idea of this protocol, they designed this protocol to provide reliable communication and delay-bounded multi-hop communication. Okay, so again, we are dealing with large networks, with many devices, with many resource-constrained devices, and we want the network to be able to self-organize, to self-manage itself, right? So for instance, in terms of communication, we want packets to be exchanged from a node to another in a multi-hop communication, right? And so there was the need for this new protocol, and this is the response that they provided with this six-stage network. Okay, particular six-stage is based on a routing protocol, which is RPL, which again deals with basically it's routing for low power and lossy networks, which is indeed the type of networks we are considering in the IoT. Okay, so here you see where the six stage is placed in a ISO-OSI-like stack. So we have the physical layer, the IEEE 802.15.4. Here in the slide is one should be 15. Still, we have the physical layer. Then on top of the physical layer, we have the scheduling, which is dealt by this six-stage protocol. And then we have all the other layers. We have the adaptation, we have routing, and the application. But we particularly focus on this six-stage scheduling. Okay, so what happens with this six-stage? How does the network is able to self-organize? So basically, we start with the root node. Okay, this JRC, which is basically the joint registrar and coordinator node, which can be seen as the root of a tree, right? In the end, we will have a structure that resembles a tree and will start from a specific node. And this JRC is the node that basically uh, grounds the foundation for creating this new network. Okay, so the JRC, what does the JRC do? So basically, periodically, the JRC needs to broadcast specific packets, which are enhanced beacons, frames. Okay, and these enhanced beacons contain the information that you see in the figure. So basically, they contain the identifier of the JRC, and then they contain information on the time slots that I was mentioning before. So the time slot duration, the number of time slots that we have in a frame, the channel hopping sequence, so basically which frequencies are going to be used, right? So when nodes receive this type of information from the JRC, they start to build some knowledge basically on how they will be able to join the network, right? So again, to sum up this part, we have the JRC, which is the starting point of our network. JRC broadcasts this basic information for other nodes to be able to join. Okay, now nodes receive this enhanced beacon and they have the basic information that they can use to establish a communication with GRC. So here in the figure, you see an example of the tree-like structure I was mentioning before, right? So you see that we have the GRC. The GRC sends this enhanced beacon, then nodes 1, 5, and 2 were the first that received valid enhanced beacons and were able to connect to the GRC. Now, since we know that these nodes have limited communication range, we cannot just rely on the GRC, right? Otherwise, if nodes are too far apart from the GRC, they will never be able to join the network. Again, because the communication range is limited. We are dealing with low power and lossy devices, right? So as soon as nodes are able to join the network, they start to broadcast enhanced beacons as well. Okay, so for instance, here in the figure, you see that node 2 was one of the nodes that first received a valid enhanced beacon from the GRC. Now node 2, as soon as it joined the network, it starts broadcasting enhanced beacons as well. And nodes 3 and 4 were able to receive these enhanced beacons and are now able to join the network, which is what they eventually did, right? So you see that we can start expanding our networks thanks to the fact that all nodes that join the network now send this type of information for other nodes to join. So here is how the time looks like in this protocol. So as we said before, we have a time slotted protocol, right? So it means that we have a slot frame, which is the one that you see here in the figure, the large one, that comprises a bunch of slots with fixed time duration. And in particular, we have the difference between the shared slot and the data slots, okay? So at the beginning of each slot frame, we have a shared slot, sorry, that is the slot where everyone can communicate, right? So in this specific slot, it means that all nodes can send their control packets. Whatever is related to control needs to be sent in this particular slot. Then after the shared slot, we have the data slots, okay, that will be second up to the end of the slot frame and will be dedicated to data sharing among the different nodes, okay? So all nodes are instructed to know at which time the shared slot will come and at which time the data slots will come. Okay, so again, whenever we are dealing with control, we need to send packets just in the share frame. So you already see where we might have a problem. If a large number of nodes are sending packets in the shared slot, it means that they are congesting the slot, right? So we have a limited number of packets that we can allow to be sent within the shared slot. If too many packets are sent within the slot, it gets congested, and then the signal to noise ratio degrades, and basically nodes are not able to receive any valid packets anymore, right? So this is where we want to focus. We need to remember that this shared slot exists, and it's just at that specific time instant, in that specific time slot, that we can share dedicated control packets. Okay, now let's go back to the joining process. Now the first problem is we have a new node, right? This node 6, and node 6 wants to join. How does node 6 how can node 6 join the network? How can it receive the valid information? Right? So the first thing is that node 6 doesn't know which frequency to use, right? As we said before, we are dealing with a frequency hopping network. It means that all nodes are using different frequencies to communicate. Okay, so the first thing is that node 6 need to scan all possible frequencies to search for the enhanced beacon that we were mentioning before, right? So at this point, let's imagine that node 6 found the correct frequency and is able to receive these control packets. So the first thing, receiving the enhanced beacon is not sufficient to be able to join the network. The enhanced beacon provides basic information, right? As we say, the enhanced beacon provides information on the ID of the sender that sent the enhanced beacon. It provides information on the time duration of the slot frames. It provides other time duration related to the slots we were seeing before. Right, so now if node 6 knows just this information, it's not directly able to join the network, but it needs to wait for a valid DODA information object, this DIO that is here. Why does the node need this information? This information is used to provide to node 6 all the information related to the network. So for instance, how to route packets where the node should forward packets to be able to reach specific type of nodes, how the tree-like structure that we see here is organized. Okay, so all the information that it needs to communicate within the network. So node 6 might be there, wait for this DIO packet. So if node 6 doesn't receive this DIO packet, it can probe the network, right? It can tell to node 5, hey, look, I'm waiting for this information. Without this information, I cannot join the network. So what node 6 does after a certain time waiting for the DIO packet, it can send this DODAG information solicitation packet, DIS. Okay, so node 6 broadcasts this type of packets, and then nodes in the network receive this DIS packet. Now, when a node receives this type of information, what it does is to reply with the DIO, right? Because it means that there's a node in the network that is not able to join, needs fundamental information to be able to join the network. Okay, so as soon as nodes receive this type of solicitation, they reply with the DIO, right? So in this case, node 4 is the one that provides the DIO information to node 6. And now node 6 is able to actually join the network, start sending information to all the nodes in the network. Right, so this type of information, like information solicitation and DIO, are shared in this shared slot frame, right? Because we said that this is the time dedicated for control packets. This is an information that the new joining node has thanks to the enhanced beacon, and therefore it will send this type of packets only within the shared slot. Okay, so as I was mentioning before, if all nodes share transmit control information within the shared slot, they might be able to congest the slot, right? And this is the case when we're talking about this attack, okay, the IS attack. In this case, we have that DIS packets can be sent by arbitrary nodes, right? Because not only joining nodes might want to send this type of packets, but also other nodes within the network are able to send these packets, right? We do not have any information on whether the node already joined the network or whether a node is already within the network. So when we are considering the DIS attack, it means that we have a malicious node that might be inside the network that is broadcasting this type of packets to all the nodes within the network, or at least in its neighborhood, right? And we say that whenever a node receives this type of packet, it needs to reply with DIO. Okay, so the goal of this attack is to increase the energy consumption of the nodes, because all nodes, we say that all nodes that receive this type of solicitation need to reply. So it means that they need to spend energy in creating and sending the packets. And also, the other goal is to congest the shared slot. What happens if we congest the shared slot? It means that all the nodes that want to use the shared slot for their communication now do not have an available space. So it means that they need to increase the number of times they need to retransmit the same packets, right? And if nodes need to transmit the same packets many, many times, it increases their power consumption. And again, this is something that we do not want for IoT nodes because they're battery limited. If they spend a lot of time for useless communication, then we are just wasting power. Okay, so this is the goal of the DIS attack. So
But is there
here,
any way of avoiding this kind of attacks, or or is there a natural way to protect myself from this kind of DIS attack?
so how can we protect from these DIS attacks? So we can either use some sort of timestamps to see whether when did we receive this last information solicitation message? Is it really useful to have this type of communication? Me as a node that received this DIS packet, do I actually need to reply to this packet because enough time has passed, right? So again, these DIS packets are used to probe other nodes and to receive updated information. But if the last time I received this type of message from a specific node is not that far away in time, then maybe there's no update in the network that it's worth reporting to the node, right? So the node can live with its current knowledge of the network. So this might be an approach to solve the problem.
Mhm.
But then there are other approaches had been proposed in the literature. This is particularly critical because this is an attack that we just discovered. Okay, it was some months ago. This is a novel one. So actually, we are now working on a practical solution for this. Again, because the DIS attack is something that was known for other types of networks, but not for this specific type of network. So the first the main solution that we are dealing with up to now is this timing consideration that I was mentioning, but we are still in the process of working towards an effective solution, right? Also because we need to remember that we do not have that much memory within IoT devices, right?
Yeah.
So the historian might not be that wide or long, right? So we cannot store that many information that relates to what happened in the past. So this is a bit challenging to be dealt with. But still, since we are dealing with packets that need to be sent to update a node on the current status of the network, on the current information of the network, then maybe we can just relax this urge for updating the routing table of a node, for instance. Yes. So going back to the attack, here is a depiction on how the attack works. So you see that within the network, we have the M node, which is the malicious one, that is broadcasting this DIS packet to other nodes in the network, which is in its neighborhood. So now all these nodes receive the DIS and start to broadcast the DIO packet. Right? So you see in the figure here in right that we have a large number of DIO packets that are flowing around the network, right? And this is what happens from a slot frame point of view. We have the shared cell and the data cell, as we were discussing. Now we have the malicious node that is performing the attack and is sending a DIS packet in the shared cell. At the successive slot frame, now we have that all nodes are replying with the DIO packets, right? So they cause congestion in the shared cell. So what is the effect of this attack? So in order to evaluate the effect of this attack, we developed this testbed. So we have the Texas Instruments CC2650 Launchpad and sensor tags, which are the devices that you see here in the figure. These devices are connected according to the tree that you see with the yellow lines, right? And then we have a malicious node in here that at a certain point, a specific time in slot frame is sending this DIS package, right? And it does this every 60 seconds. So here you see the impact of the attack. We see the impact both in terms of synchronization time, so for nodes that are already in the network, so how much is the time increase for all nodes to get updated information related to the network structure. Here you see the increase in joining time. Okay, so we have new nodes that want to join the network. If the network is currently under attack due to this DIS attack, how much additional time do nodes need to join the network? And last, here you see the additional energy consumption of all the nodes. Okay, so basically you see in the blue bar, the blue part of the bar is the evaluation without the attack, whereas the white striped band is the additional time or energy consumption when we have an attack. And we see that actually this type of attack is really critical for this type of network. In particular, we have an increase of energy consumption which decreases also the lifespan of the IoT nodes. So now I was supposed to talk about the countermeasures to this attack, but as I was mentioning, at this point, the best countermeasure we have is this consideration time. We might consider the fact that we receive DIS packets with certain identities, and based on the identity that we have in the packet, in the DIS packet, we can decide whether it's the case or not to respond with the DIO packet. This should decrease the time needed for synchronization, and it also should decrease the amount of energy wasted for this type of communication. An issue that is still open is the joining time. So if we have an outsider that is sending this type of packets, just having the ID of the node that is sending this DAS packet might not be sufficient because a clever attacker might be able to modify the ID packet per packet, and this might be a bit challenging.
So what
Uh,
x axis represents here? Is it the nodes or different nodes or
can you repeat, please?
so? What's the x axis
Ah,
represent?
yes, X. Yeah, sorry. Yeah, in the X-axis we have the node ID. So one is the first node, two is the second node, so on and so forth. So here we see the increase in terms of time, in terms of energy per node.
Yeah, that's
So
what
this is
my question was, because I see a general trend of increasing for in terms of time for attack and without attack both.
Yeah, this is due to the to how the network is configured. So you see
Okay.
here we have the node one, then node two, then node three, node four, five, six, seven. So we cannot just look at their behavior in terms of what is happening in the x-axis because it's each node is, I wouldn't say independent, but we cannot expect a trend over the what happens in the x-axis. Yes. Good. So this is what happens in terms of attacks to protocols that we use in the IoT. But then, as we were mentioning, we are dealing with wireless communications. Right? Wireless communication means that nodes can simply transmit. Right? And if we have random nodes that are just transmitting their traffic, that might cause a level of interference that might not be manageable by legitimate devices. Okay, so again, in terms of channel hopping, what happens as we discussed previously? Okay, we have each node that needs to select a frequency, a channel, where at each time slot it wants to transmit. Okay, so in terms of channel hopping, we can see channel hopping as a black box. So the node communicates with this black box, and out of the black box, we have the transmission frequency that the node wants to use. So this channel hopping is really useful when we're dealing with IoT devices, and in particular with wireless communications. Okay, why is that so? Because if the node is able to dynamically change the channel, it might be able to mitigate the interference caused by other devices in the network, right? If all devices use a frequency that is sufficiently far apart from the successive frequency in terms of this tech, if each device is using a different frequency, then they're not interfering one another. Okay, so they're simply transmitting on different channels, not disturbing one another. Still, these channel hopping strategies might be different, might be simple, might be a bit more complicated, but still, we have this black box that as output should provide the decision on which channel to use, right? So we might have sequential channel hopping. So basically, the device is first selecting channel one, then channel two, and channel three, blah, 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 to channel n, then start again from channel one in a sequence. We might have random channel hopping, which means that the black box is basically a random number generator, which generates an integer between, let's say, 0 and n minus 1. Okay, so basically provides a random channel at each selection time. Or we might have some form of smart channel hopping. So smart channel hopping means that this black box might implement some game theoretical framework, might use machine learning, it might use artificial intelligence or deep learning. It might be based on deep reinforcement learning, for instance. Okay, so based on how the device interacts with the wireless environment, this black box can learn something, can in particular learn what might be the best channel hopping strategy for the devices to maximize its effectiveness in terms of communication. Still, if the channel hopping strategy is not it's too simple, let's say, or it's simple, an attacker might be able to learn the channel hopping strategies used by a device, right? So let's imagine that we are dealing with this sequential channel hopping. it might be straightforward for an attacker to spend some time and figure out that the user is just selecting subsequent frequencies at each time, right? So now if the attacker is able to learn the sequence of frequencies used by the legitimate device, it might be able to jam the communication, right? To create an interference over that specific frequency such that the legitimate node is not able to deliver a packet at the legitimate receiver anymore. Right? So if we want to design an efficient strategy for this, we have two fundamental requirements. First thing is that we do not want to make any assumption on the victim's open pattern. So the victim might do whatever it wants, right? It might be random, it might be sequential, it might be based on game theory, it might be based on machine learning. Okay, whatever. We don't really care. This is something that we want to learn by looking at how the victim is behaving. The other important requirement for an efficient attack is to be continuous in time, right? If the attack just works for a couple of seconds, then it needs to stop for 20 seconds in order to learn the victim's opt-in pattern, that it would not be an efficient attack, right? So what we did in order to propose this efficient attack is to use a multi-armed bandit framework. Okay, and thanks to this multi-armed bandit framework, we are able to efficiently follow the victim's channel hopping strategy. Why multi-armed bandit and not deep learning, for instance? Well, the problem with deep learning is that as long as the victim is using a specific hopping pattern, then machine learning is good. We learn it once and then it will work forever. But then, if the victim realizes that there's an attack going on and it decides that it wants to change the hopping pattern, then the machine learning needs to stop for a certain period of time, learn the new pattern, and then apply the attack. And this is not something that we want, because if we want to deliver an efficient attack, we cannot just afford to stop for a certain period of time and wait for the attacker to learn the new pattern. Okay, so thanks to this game theoretical framework, we are able to deliver this type of attack. In particular, we exploit a Markov decision process. I will spare you the math on how this works, but basically what we are estimating are state transition probabilities. And we have this sort of reward framework where we update the a posteriori probabilities based on the effect of the attack. Okay, so basically, if the state transition probability is good and we are able to deliver the attack, then this state transition probability gets rewarded. Otherwise, it gets a penalty. Okay, so also in this framework, we need to learn something. We need to learn probabilities, but this can be continuous in time. We can just update probabilities as the um, as the attack runs. Okay, so we have other attack strategies, of course. This multi-arm bandit is our proposal, but there are also other attack strategies. So what we wanted to show is that through the multi-arm bandwidth, we are able to deliver a more efficient attack. So of course, first attack might be random channel hopping, where the attacker just randomly selects certain channels to jam. Then we have reactive channel hopping. So basically, the attacker waits to hear communication on a specific channel, and if it hears a communication, it delivers the jamming attack. Okay, sorry. Then, as we discussed before, we might have frameworks based on deep reinforcement learning, where the attacker just learns the victim's channel hopping pattern. And then, in order to compare our attack with the best possible solution, we have the Genie-aided attack, which basically assumes that the attacker perfectly knows the hopping pattern of the victim. Okay, this is of course something that is not possible in reality, but it's just to have a comparison with the optimal approach. So here are the results. We see that thanks to the our attack is the purple one. So you see that basically what we have is that we are able to reduce the packet delivery ratio of the victim. So it means that the victim is not able to deliver on the packet. So packet delivery ratio is here. the ratio between the successfully delivered packets and the number of packets that have been sent in total. And the orange one is the optimal approach, the gene-aided approach. And we see that the purple one approaches the orange one. Instead, when we are dealing with deep reinforcement learning, the blue one, we see that the attack is not always very effective. Here, when it goes up and then down again, and then up and then down again, it's because the attacker needs to learn the new pattern of the victim. Okay, so in terms of countermeasures to this attack, again, this is something that we are working on. The idea would be to provide true randomness to the hopping pattern of the legitimate device. Right? Because if the attacker is not able to learn anything out of the hopping pattern of the legitimate transmitter, then it's not able to update the probabilities and therefore be able to predict the next channel that the attacker needs to hop. Okay, so we are working towards this true random channel hopping that will provide a situation where it is basically impossible to learn anything out of observation on the behavior of the user. Okay,
What,
and
sorry, what the right
yeah,
figure represents here in the graph is success
yeah,
rate.
sorry. Success rate basically is how much the attacker is successful. So basically, how many times does the attacker find the correct communication channel? Okay, so how many times the prediction is correct? Not only that the prediction is correct, but also the fact that the attacker should be able to generate a signal to degrade the signal to noise ratio at the point where the receiver is not able to receive the packet anymore. So this is something like 1 minus the figure on the left, right?
Okay.
Opposite, sorry. Something like this. Good. And then the last point that I was mentioning is the one of privacy in the Internet of Things, which is, again, a challenging task when we're dealing with IoT. In particular, when we are dealing with drones. Okay, so when we're talking about drones, we have a specific protocol that has been proposed and needs to be used in drones, where basically drones need to broadcast information that report information on their identifier, okay, their unique identifier, their location in terms of altitude, longitude. Okay, so they need to provide full information on who they are and where they are. So, of course, from a user's point of view, this is not good, right? The user doesn't want to provide all this information to everyone because everyone now is able to receive this kind of packet to understand the content of the packet and therefore be able to see who's around in the area, right? But from a critical infrastructure point of view, this will be really useful. So let's imagine we are talking about an airport. An airport needs to have this type of information because it needs to understand whether a drone is approaching, right? So there have been many examples of drones jeopardizing the safety of airports. Famous example is the one in Gatwick, where we had that really a huge disruption on the service availability due to the fact that drones were there in the airport, right? So it is fundamental for critical infrastructure to have this information on drones. So here we have an important trade-off. We want to guarantee privacy to users because if we don't guarantee privacy to users, no one will use the technology. But on the other hand, we should not prevent the critical infrastructure to have basic information on who's using devices and what they are doing with devices. Right, this is a depiction on the system that we are considering. We have John that is sending these remote ID messages with all the contents, and then we have a critical infrastructure. Okay, it might be an airport, it might be a military base, might be whatever type of critical infrastructure, that needs to understand whether a drone is approaching. Okay, so around the critical infrastructure, we can define two areas. The first one is a no-fly zone, where definitely no drones should be there. And then we might have another area. Okay, so if the critical infrastructure detects that a drone is in the other area, it might raise an alarm. Okay, and if the drone continues to approach towards the no-fly zone, it might be the case where it needs to be taken down. So in terms of attacker, so the attacker is the pilot of the drone. We might have three types of attacker, or at least the ones that we consider. We have the unaware invader, which is basically the a random guy that is flying the drone and is unaware of the fact that he's approaching a critical infrastructure. Okay, so this type of attacker is not doing, I mean, it's doing nothing bad, right? It's just unaware of the fact that there's a critical infrastructure in there and still is causing problems to the critical infrastructure. It might raise alarms on the critical infrastructure side. Then we have a rookie pilot attacker, which basically is an attacker, but we assume that it has no capabilities of modifying the firmware of the drone, for instance. Okay, so it has basic information on how the system works, but it's not able to modify how the drone is broadcasting packets, for instance. Okay, so this might be dangerous because we have an attacker. We have someone that is flying the drone towards the critical infrastructure and may be able to drop a bomb, for instance, at the critical infrastructure side, right? So this is really critical. And then lastly, we have an eavesdropper, which is not the pilot, but it's just someone that is on the ground and is listening on the communication of the drone. Right? As we said before, if the drone is just broadcasting information on its ID and its location, someone is on the ground might be able to track specific drones. So let's imagine, for instance, that Amazon is delivering items thanks to drones. Then if someone is able to infer what is the ID of the Amazon drone, it might be able to follow this drone and to take it down and therefore steal whatever the drone is scanning, right? So that's not good at the same time. So we need to provide privacy to users, but at the same time provide means for the critical infrastructure to defend against these first two types of attackers. So what we did is to develop this differentially private remote identification. So basically, again, here I spare you the math, but the point is instead of transmitting the clear text information on the location, we provide a sanitized version of the location. And this sanitized version is based on differential privacy. So basically what we do is to add to the true location some random values that are generated according to a specific distribution and with certain geometrical properties. As for gene distinguishability, I'll leave you here the name if you're interested. But basically what we are doing is creating a bubble around the drone and a bubble out of which we take random locations. And therefore, we do not provide the correct information on the location of the drone, but a random point in this bubble of locations around the drone. Okay, so this provides the privacy guarantee to users because we are not just sending the clear text information on the location. We are providing a sanitized version. Let's say that we are providing random location values, random, but just in the sense in this bubble that I was mentioning around the drone. Why don't we provide just random location values? Well, again, because we need to provide to the critical infrastructure means to defend against possible attacks from drones. So again, this provides the privacy guarantees to drones, but then we add also the framework to be deployed at the critical infrastructure. So what does the critical infrastructure do? Basically, it starts receiving information from a drone. Then it has a time window out of which it collects a lot of packets. And basically, what the critical infrastructure does is to average these different sanitized locations. And if the average of these values is within a range, then the critical infrastructure raises an alarm. Okay? So now the critical infrastructure doesn't have any mean to know where the drone exactly is. So in the current implementation, the best thing we can do is to refer to a trusted authority, a trusted third party. So as soon as the critical infrastructure detects a possible invasion, it communicates this invasion to the trusted third party, which has the ability to check where the drone actually is. Okay, so we have a third party that is able to know the exact location of the drone, but this is just something that we have in there. This location will never be shared with anyone. The third party will keep it for itself and will just either confirm or deny the possible invasion reported by the critical infrastructure. Okay, so here we have the results that we obtain with this framework. So basically, on the left we see so this epsilon and d are the privacy budget that the drone has. Okay, so these are two parameters that we can tweak when dealing with the differential privacy framework. So when creating the bubble that I was mentioning, and so here you see how the average distance from the true location and the reported location changes, right? So by changing these parameters, you see that when epsilon is large and d is small, we report a location that is more or less the true one. When instead epsilon is small and d is high, we report a location that is really far from the correct one. Instead, here on the right figure, you see the true positive rate, false positive rate, which basically means how many times does the critical infrastructure detect an invasion, which is an actual invasion, and how many times does the critical infrastructure detect an invasion, which is not an invasion, right? So here you see how the performance change with this parameter used by the drone. Okay, so here we have a fixed time window of 10 seconds. And out of 10 seconds, we collect packets, we take the average, as I was mentioning before, and then detect whether there's an invasion or not. Of course, the quality of the average that we get depends on this D parameter, which is the privacy budget of the drone. So we see that if D increases, so from the left figure, we see that if D increases, we have that the reported location is far from the original one. And this is reflected in the performance of the Icarus framework and the framework of the critical infrastructure. Indeed, if D increases, the true positive rate and false positive rate decrease. Okay. Um, so this is a basic solution that we created to account for this trade-off. We want to guarantee privacy to users, but at the same time, we want to use the information reported by the users. So to sum up this talk, we've seen how security and privacy may impact on the Internet of Things network, and we also see why this might be really challenging. It might be challenging to provide security and privacy to IoT devices. And in particular, we've seen that these are recent results. It means that we have the technology, but we are not at the point where we can safely use the technology. There are security problems that may arise in time, and to which we need to find specific solutions that are targeted to the resources and the capabilities of IoT devices. So I thank you all for your attention. Here is my mail in case you have any questions, or feel free to contact me for any questions related to this presentation. Thank you again.
Yeah, thank you, Alessandro, for your nice introduction on and also on new research that you are doing in terms of privacy and security. I think I have just one question on your previous slides on yeah. So here, I guess it looks like the TPR rate is dropping at some point, or is it the performance is going worse than the previous?
Yeah, so yes, the performance are decreasing at a certain point due to the fact that the drone is reporting random values that are really far apart.
Okay.
from the correct one. So basically, at this point, we are providing more privacy to the drone because it's reporting locations that are really not the correct one. So the user is happy, right? But the infrastructure is not happy about this because it's losing in terms of performance of true positive rate. It's not able to, it's not as good as it was when the was smaller to detect invasions. So
Yeah.
this is actually to show the trade-off between the privacy that we can guarantee to users and the usability of the data that we have. And still, we want to use data, right? We cannot just simply rely on the fact that users are not malicious. But yeah, it's
Yeah.
difficult to do to make everybody happy at some
You
point.
cannot get everything. Yes.
Yeah,
I don't think so. I have so many questions on Discord. So far the questions I repeated. And thank you again, Alessandro, for joining us. And we
thank
hope
you.
we will get you also for our next year's course, if
Will be my pleasure.
if you are available, of course. Yes.
Sure thing. Sure. Thanks again for inviting me. It was my pleasure, and definitely would be happy to be here also next year.
Yeah. Thank you.
Thank you.